Okay, so this is Psych 3280 for week 7, neural-based subconsciousness. And this week, we are going to talk about higher visual areas and NCC. So just to start from the recap of the last week, week 6, we first introduced the concept of the NCC, neural correlates of consciousness. And that is the minimal set or a set of neurons that is sufficient to give rise to a particular conscious person. And this is a hypothetical entity in the brain, and here a particular conscious percept may be something like visual motion of particular direction, particular speed, and so on. And then we also introduced empirical NCC search strategies from the Chris Frith's paper in TICS. There, it articulated that it is most efficient to do that by fixing either sensory input or conscious percept or behavior output while varying the others. And then I went through all the details of the tables. And I suggested that utilizing this concept would be very useful for your final writing assessment to propose a new empirical research for consciousness. Empirical research for consciousness. Okay. Also, I covered several topics as well in last week. One is that whether the NCC can be found in V1, and there are several reasons to say that V1 is unlikely candidate for the NCC. And one of the reasons is that non-conscious orientation dependent adaptation using this demo of the crowded orientation stimulus. I tried to show that it is likely to be mediated by V1, but this adaptation does not require conscious experience. Therefore, V1's activity that is sufficient to generate this adaptation is not really sufficient to generate conscious percept of this orientation. And the other arguments include that the dreaming suppresses V1, or blinks and eye movements are still is reflected by the V1 activity, but our conscious experience usually do not reflect the eye blink or eye movements. Okay. So that's the one of the several reasons for V1 as unlikely candidate for the NCC. All right. And then on the other hand, I argued that MT, middle temporal area, responsible for motion perception, is likely to be also the neural correlates of motion qualia. And the reason, one of the reasons is that motion after effects, that after adapting this, expanding motion stimulus, the Buddha stimulus, stationary Buddha stimulus probably felt like shrinking or the other way around. And these are mediated most likely by empty neurons. And for this type of motion after effects to work, it requires visibility of the motion stimulus, especially for those complicated motion type. And most likely, these motion after effects are mediated by more empty neurons. So both, after effects are requires MT, and MT activation inferred from motion after effects are sufficient to generate motion qualia. Also, I reviewed some of the literature on the lesions of bilateral MT, which is very rare, abolishes motion percept and make the life almost like stroboscopic or disco-like experience. And also neural recordings done by the Newsome teams in Stanford and other US areas are very convincing that momentary fluctuation of the neuron activity correlates with monkey's perceptual report, especially with the random dot motion, and also microstimulation of the MTs by virtue of the MT being the columnar organization, also biases monkey's perceptual reports. And taken together, all these imply it's likely that the MT neuron activity and so connectivity is sufficient for motion qualia. So this week, week 7, we will review the evidence for higher visual areas as the candidate for the other content-specific NCCs. And I will introduce powerful tools for consciousness research. Okay, and that includes binocular rivalry and continuous flash suppression and the decoding of the neural activity. So in terms of the learning objectives specifically, I'm going to, you are supposed to be able to answer the question of what are the evidence supporting the claim that higher visual areas are the NCC. And for this matter, the Quest for Consciousness chapter 7 and 8 are the recommended readings. And also, what are the phenomenological and behavior characteristics of binocular rivalry? And how did the researchers establish a binocular rivalry paradigm with monkeys as participants? And what are the implications of the NCC studies using binocular rivalry? And for that matter, Quest for Consciousness chapter 16 is going to be very useful. Okay, so let's first start with the V4 as the first target areas of the higher visual areas candidate for NCC. Okay, V4. So as I reviewed in week 5, each areas have a distinct connectivity pattern in the laminar structure. So if it is receiving the forward input from the lower areas, it tends to receive the input at the middle layer, layer 4. And then if it receives the feedback connection from other areas, it tends to receive the synaptic input at the lower or upper area of the layers. And based on this type of the layer structure and also connectivity patterns, people have constructed this Van Nessen diagram for the visual hierarchy. And so far, we have basically covered the retinal neurons, LGN, lateral geniculate neurons, and V1 that starts to possess the orientation selectivity, and then V2 for the illusory contours. And from here, as you can see, the diagram becomes very, very complicated. So V2, after that, V3 or V3 dorsal, V3 ventral. So this left side is more like a dorsal areas, the areas that goes the side of the back of the brain. And then this right side goes to the ventral. Ventral means, on the very side of the brain. And here, the MT locates more or less intermediate between the ventral and dorsal. So that's here. And that's what we focused last week. And then V4 locates into the ventral version, ventral areas, and around the same hierarchy as MT. So V4 is still a part of the retinotopic area, means that the input from the outside visual areas, visual input is more or less faithfully represented in terms of relations. But remember that all of these are distorted in terms of the cortical magnification and the receptive field size. So fovea of the left visual field is represented in this all right hemisphere, okay? All of this is the right hemisphere. And for monkey and human, and it's compared. And then right hemisphere is unfolded. And if you don't understand it, you go to week 5 lecture video again. And then the left visual field upper part is represented by the ventral part of the V1, V2, and then V3, V4. And then this side ventral part, this is a ventral, and then this is a dorsal part. And then MT is intermediate, is represented many times. Okay, and then V4 is a part of the ventral areas, and this has been suggested as an particular neural correlates of consciousness before. So one of the most compelling evidence for the V4's involvement of the consciousness has been this color qualia. And here I'm going to review one of the case reports of the patient AR, who was studied around 2000 by Jack Gallant's group. And here, again, this is a radiological convention. So the right side of the brain is represented in the left, and left side of the brain is presented in the right side. Okay, and this triangular points the highly restricted lesion in this particular patient. And this patient, after some lesion, they lost some color perception. Okay, and however, initially, and also even after he was tested with a clinical trial, he's quite remarkably, as Crystal Cox's book says, that this patient and others like him do not notice that they see in gray in one part of the visual field and in color in another. So here, this AR's case is the right and the ventral area, and that corresponds to the visual field of, this is a left visual field, so this is a fovea. Upper part of the visual field is affected by this one-sided brain lesion, and as a result, he was tested as achromatopsia, or loss of the color only in here but not other area. That's very interesting situation. And the more interesting thing is that this patient do not spontaneously notice that it is gray. And this is actually a highly profound kind of concept in consciousness research. If you don't have a capacity to experience something, you actually do not notice that it's not there. It's very difficult to understand, but if you think about your experience in the back of the head, that's something that you can imagine. You don't have anything to experience in the back of the head, and that's the reason why you also don't notice that you don't usually see, in the back of the head. However, if you have a particular part of the vision that can possibly experience something, and you are not experiencing in that particular location, let's say, if I cover my, right eye here, then I can't see it, some part of the region, right, far right here, which is not usually, visible. And if that is the case, then I can notice that, oh, I'm not seeing, and that there is abnormality here. So conscious experience is all about, in the end, the possibility of experience. And this is very important, which will come back in integrated information theory in week 10. And this is also important for psychological and also clinical kind of insight for how to rehabilitate a patient. Possibility of experience is quite important. Okay. So let's go to this case report. So the task that Gallant devised was a hue discrimination task. And then here the hue is very basic kind of, concept of the color. So color can be described in many different ways, but one of the ways to describe the input to the eye in terms of color corresponds to consists of the hue, saturation, and brightness, B, or sometimes called using nu or V here. And when the brightness is low, then it becomes black, and if it's too high, then it becomes white. Okay, and the saturation means that the degree of the colorfulness starting from center to the periphery. Okay, and then the hue describes the variety of the different colors. So usually red is located in opposite side of the green, and the blue is opposite of yellow, and so on. And there's this coloring described like this way. And then the color hue discrimination task can be constructed such a way that maximum hue difference is 180 degree. And normally we can distinguish the difference between the two colors, such as this orange and the yellow, or small shade of the green and blue, and so on. So it's a few degrees and so on. However, this patient, when tested with this type of the task, showed the dramatic performance degradation. So these UR, LL, and LR corresponds to the performance at the 3D opposite, unaffected visual field. So here, this is a UR, this is the LL, lower left, and this is lower right. And then there, when the hue is red as a baseline, they can detect the difference reliably at a few, 10 to 20 degrees of the difference in the hues. And that's not that different from the other patient under the certain, experimental conditions. Okay, and then this is the case when the green is used as a baseline. On the other hand, the upper left here is clearly, bad. So 100 degree means that if the baseline is red, when the color looks, was presented around here or there, yellow or blue, then patient can say that, oh, it looks different. Okay, so that's the kind of the deficit this patient has. And remarkably, when this patient was tested with some kind of object, let's say colorful patch here, moving from here to there to here, it seems like this patient will not perceive the fact that the color has gone from colorful to gray within this, and then again colorful. But again, as I said, if there is no possibility to experience the difference, then it's very hard to experience the difference, at least from the intrinsic viewpoint of the patient. So that's very interesting observation. Okay, so one of the controversy about the color and color qualia and B4 is that when the monkey physiologist has lesioned monkeys V4, then they don't really show the color deficits. It's very different from MT lesions and motion qualia. So it's been controversial. And so one of the breakthrough that came around the end of 20th century is the test for whether the V4 is really the NCC for color or not. And can you imagine what was one of the tests that they did? So it's a color after image. That's one of the technique that they can use. Okay, and then so what they do, they did was to use the after image technique or After Effects technique that they use for MT from last week, and then they applied it for the color case. So just a demo for this effect. I want you to fixate at center and then look at this screen. And that's the similar kind of after image demo like last week, but it's a slightly different. So here I'm going to change blue and yellow, left and right, and then but keep the red and green upper visual field. Then what happens is that after image of the blue and yellow cancels out each other, but the green and the red should be staying there. Okay, 3, 2, 1, 0. Okay, so for me, it works really well and it continues there. Top left is blue and then top right is purple. And the bottom left and the bottom right is completely, gray. So this type of the experiment can be utilized to look at whether the color after image is generated in V4 or not? So what happened? So Hajikani and colleagues did this experiment using fMRI in humans, and it turned out that all these color after image effect comes from not from V4 area here, and in fact it was found in V8, what they call the V8. So usually people term it, in the order of the discovery of the visual areas, and the V8 is probably the last one to be reported over the last 10 years or so. But V8 area seems to be the ones that reacts to color image. And here is this, color code for the strengths of the after image response. So what they did is once again, doing this alternating color time from 48 to 96 seconds, 48 seconds, like blue, yellow thing. And then when it turned off, then the areas, V8 areas response became weak, like immediately around the baseline. On the other hand, if the same duration of the exposure to the constant color was followed by the gray fixation, then there is a huge response at the offset of this, stimulus, corresponding to our own, color after image. And when they averaged all these, response and subtracted the fixation for these two situations, then they found that, V8 responds significantly at the onset of this color after image induction. So that's one of the evidence for the V8's involvement for the color experience. But also another version, another type of the evidence can be found from this type of microstimulation experiment. Here, the epilepsy patients who are, are inserted with lots of electrodes to locate their epilepsy location. And this is the small subset of the ventral surface of the brain. So this is the brain looking from below, and then upper part is eye and the frontal areas, and the back part is sort of B1 here, B1. And then the ventral surface of this right side and the left side of the brain is enlarged here. And then what they found was that the areas that were covered by these electrodes, which happen not to be corresponding to his location by epilepsy, generated the responses preferentially to the color image around these electrodes. And here, these electrodes preferentially responded to the face stimulus. And I'm going to come back to that later in this lecture. But anyway, so let's take a look at what happened to him when he was stimulated by this particular electrode 178 and so on. And a pair of the electrode 178 and next to each.
So he's now looking at a screen or sort of one of the meaningless object, and then see here at the bottom right, you see the microstimulation delivered into the color area of his brain, and that appears as a sort of artifacts of this EEG recording. So EEG recording within the brain is represented in a bunch of lines that goes from left to right, and each of the height corresponds to different channels of the recording. And some of them are color responsive brain electrodes, and some of them are not. But delivering electrical stimulation generates lots of artifacts. So here's the artifacts. And then he's nodding. And then it's terminated right now. And then he's going to describe his experience here. So he's actually a Japanese person, so you won't understand what he's saying, but the subtitle means is a good translation of what he's saying. Basically, he's saying that during this stimulation, left side of his vision becomes colorful. And also here, the same kind of stimulation, and then it's already terminated. And then looking at the face, and with respect to the nose, when he was looking at his left side starts to become like a rainbow color. Okay, and regardless of what kind of object he's looking at, it's always like the left side of the things that becomes colorful.
Okay, so in summary, this first part of the lecture showed that V4 or V8 is a likely candidate for the neural correlates of color qualia, and evidence comes from lesions after image in fMRI and electrical stimulation. And here again, the question comes to the same kind of thing as the MT situation. What is special about the neurons in V4 and V8 in generating color? And if you look at neuronal spiking behavior or biophysics or connection, it doesn't look like they are significantly different at the first look, but they are most likely different. And these local connectivity and local property of the neurons are likely to be the factor for generating color on one end and motion on the other end. But we currently do not have any theory, precise theory, except for most likely IIT integrated information theory like scenario, which we are also working on, is able to explain why it is that V1, V4, or V8 neurons can generate color while MT neurons can generate the motion. And this is, in fact, the hard problem of consciousness. Okay. So, but before going further, we will go into the further evidence to look at the higher visual areas and its relation to the content-specific NCC in the next part of the video.